First, good afternoon. Welcome to this webinar. My name is Hui Yang. I am an associate professor from Harold and Inga Marker's Department of Industry and Manufacturing Engineering at the Penn State University. Thank Pentab for the invitation. It's great to be here and share some of my research on Internet of Things and smart manufacturing. So today, I'm going to talk about the Internet of Things and data-enabled innovations for smarter manufacturing. So let's first have a look at the Internet. So Internet, as everybody knows, is widely used in the world. And as we can see from this figure, Internet users in 2015 as a percentage of the country's population. So in the United States, 70 to 79% of the people are using the Internet. And Canada, North America, Canada 80 to 89%. In Asia, China is a little bit lower. It's 50 to 59%. But the population base is much bigger. China has 1.3 to 1.4 billion. So 50% is around 0.7 billion people are using the Internet. So this Internet technology establishes a huge network in the world for communication. So as we can see, people are taking their phones to check the news and to communicate with friends in the Facebook. Now let's have a look at the evolution of the Internet. In the pre-Internet phase, we have human to human communications. So people are using the fixed and the mobile telephone and SMS to do the communication. Then when the Internet comes, we have smart networks. So the smart networks give us the World Wide Web to share the content. So people can write emails, share information and entertainment. And then we have smart IT platforms and services. That is the era of Web 2.0. It's also Internet of Services. So we have e-productivity and e-commerce coming. And in the past 10 years, social media is pretty big. And we have Skype, Facebook, and YouTube. And that's the Internet of people based on the wide application, wide use of smartphones. And what will be the next era? That is the Internet of Things, machine-to-machine communication based on smart devices, objects, and data. So we can do the identification, tracking, monitoring, metering, and automation, actuation, and payment. This Internet of Things. So smart data and ambient context information are connected, can be connected in the manufacturing environment. So we are moving from the Internet of People to Internet of Things. As we can see from this slide, in 2010, world population is about 6.8 billion. Connected device, 12.5 billion. By 2020, it is projected that the world population will be 7.6 billion, but the connected devices will increase to 212 billion. So we are moving from the Internet of People to Internet of Things. So people connect to the Internet. And now we have things connect to the Internet. And what will be the future? Things connect to things, and they can communicate. We can have a Facebook of manufacturing things. So large-scale IoT systems brings big data, that is a huge amount of data. And how do we extract useful information from the data and then derive new knowledge about the complex engineering systems? Then leverage the information and the knowledge we gain for the optimal design, monitoring, and control management of those systems. So we are going from data to insight to action. And that is the framework called the DIK UW. So we're going from data to information, to knowledge, to understanding, and to wisdom. And in each area, we need a different kind of methodology, like data security and data storage, data aggregation, and data visualization. And then we need to have for insights, the methodology we needed are machine learning, analytics, and visualization, data science. For control and management, so in industrial engineering, we do optimization algorithms, decision making, and decision science. So we're trying to connect from data to operations management. So data to insight to action. So what is the future of manufacturing? So IoT for smart manufacturing. In the past, this is manufacturing, heavy pollution manufacturing. But what will be the tomorrow? Tomorrow we will have smart and digital manufacturing, okay, and advanced sensing, big data, system informatics, e-design, modeling and simulation, high performance computing and optimization. So the potential economic impact of IoT in 2015, as we can see from here, for the factory. So it's about 1.2 to 3.7 trillion dollars. So the applications include operations optimization, predictive maintenance, inventory optimization, health and safety. But this part is only for smart factory. Manufacturing is more than factories. And we also have work site, also has health and safety of the workers, equipment maintenance. So this is reliability engineering in industrial and system engineering. And IoT enabled R&D, and also automotive industry is also part of the manufacturing. We have electric cars and also traditional cars. So they can be, we can have condition-based maintenance and reduce the insurance. And also this outside, the supply chain is also part of the manufacturing in large context for manufacturing systems. So logistics and navigations. So as we can see, manufacturing actually has biggest impact by the Internet of Things technology. So IoT for smart manufacturing, as we just discussed, is about 1.2 to 3.7 trillion of economic value annually by 2025. So the values actually can come from supply chain management, operational efficiency, predictive maintenance, or inventory optimization. Those are only some examples, and go beyond that. Smart manufacturing will create value from data, streamline design processes, optimize factory operations, and mitigate and reduce the risks we have in the supply chain management. So also, now let's have a look at the Internet of Things and the connection with human and work. So National Science Foundation actually have a big initiative to try to push the human technology partnership, improve worker performance, increase workplace safety, and increase career longevity and job satisfaction. So as an example, for example, the safety, IoT can be applied to device, right, and this door of the car and the robot, and also the workers, the badges. So if the robot or the car, they are moving too close to the workers, and we can send an alert or even stop the equipment so that to prevent potential injuries of the workers. So this is how we can do the human robotics and the technology and different kind of manufacturing technology, the partnership for safety, work safety, and also try to improve the human performance in the working environment. So that's a potential direction. So we have been talking about smart manufacturing. Now let's have a look at the definition of smart manufacturing. So what is smart manufacturing? Smart manufacturing, this is Sesame. Sesame is Clean Energy and Smart Manufacturing Institute. And I have attended several Sesame meetings and to talk about smart manufacturing and how Penn State can be involved in smart manufacturing. So smart manufacturing enables all information about the manufacturing process to be available when it is needed, where it is needed, and in the form that it is needed across the entire manufacturing supply chains, complete product life cycles, multiple industries, and small, medium, and large enterprises. So you may note the when it is needed and where it is needed, and most importantly, in the form that it can be easily comprehensible by the human, okay, across the entire manufacturing supply chains. So recently we had one review paper on Internet of Things for smart manufacturing in AI transactions. So what we are proposing is in the as we can see here, in the physical world, we have machines and we have manufacturing process. And in the right side, we have the cyber world and we can have virtual machines. But how can we bridge the cyber and the physical world? So that is because of the sensor networks and IoT, Internet of Things sensors. Okay, we have unprecedented access to data. So this makes it possible for us to simulate the physical world in the cyber world, or map the physical things to the cyberspace. And then we can run the optimization or the decision-making, diagnostics, and predictive maintenance algorithms in the cyber world, and then feedback the insights and actions to the physical world. So smart manufacturing is integration, seamless integration of cyber and physical space. So now let's have a deeper look into the cyber physical systems. So now let me take the Uber as an example. For example, in State College area, we have cars, they are running on the street. But whenever you get your phone out and try to call Uber, you will see virtual cars on the screen. So this is the physical world, and this is a cyber world. And the cyber physical integration makes the success of Uber. But what will happen to manufacturing? That's something we need to think about. So 20 years ago, we have automated manufacturing, right? High-level automation is used by General Motors and Ford, all the big automotive manufacturers. And we have engineering innovations. So what is the difference between automated manufacturing and smart manufacturing? So automated manufacturing is more on the engineering innovations, but smart manufacturing is more on the data innovations. Smart manufacturing is not just automating the manufacturing flow. It is more about the data-driven autonomy, evolution, simulation, and optimization of the manufacturing enterprises. So the smartness level really depends on the integration between physical space and the cyber space. So that is the smart manufacturing. Okay, so far we talked about the Internet of Things, smart manufacturing, the evolution of the Internet. Now let's have a look at a specific case study on how can we leverage the data we collected from manufacturing environment for optimizing the quality of the build in additive manufacturing. So this case study is about sequential optimization of the 3D build quality in additive manufacturing. So additive manufacturing is 3D printing we talked about in the layman terms. So we have three papers on this case study. The first one is about multifractal analysis of imaging profiles for the defect detection and characterization. And the second one is how can we go from process condition to build quality through modeling and monitoring of the in-process layer-wise images. So we go from defect detection and try to study the process settings. And also, the third paper is about Markov decision process for image-guided additive manufacturing. So we go from data and to information to knowledge and try to do the decision making and the optimization of the additive manufacturing. So before I dive into the optimization part, let's first have a look at what is the additive manufacturing. Additive manufacturing, this is a CAD model, computer-aided design model. And we can put the CAD model into the additive manufacturing machine. And in this machine, we're going to print the part layer by layer. We spread the metal powders and then use lasers to fuse one layer of the powder. Then we will form one layer of the 3D part. Then we lower the powder bed and we spray another layer of the powder. And then we do the laser sintering again. So in the end, we will get a metal part. Okay? So this is a 3D printing layer by layer. We spread the metal powder and we print it again, and we spread it again. So in the end, we get a 3D printed metal part, and we can get it out. This is out of the chamber. This is additive manufacturing. So, but there are significant challenges in additive manufacturing. This is one study with from my colleague, Dr. Tim Simpson, and also the Sims 3D researchers and scientists in Sims 3D. So we did one study on the same CAD model. That means the same design and the same machine and the same process settings. But we got a very different results. Okay? And we printed 7 metal parts. Only 3 of them are defect-free. So 4 of them, they have defect, different kind of defects. So this is one test part with defect layers over here, and this is a second test part with malformed things over here. So as we can see, we are trying to do the same CAD model, same process setting, same machine, but the process still have uncontrollable variations. Now, how can we tackle those challenges in additive manufacturing? So we propose a new idea on the image-guided manufacturing. So this is a laser powder bed fusion process, and it's also called LPBF process. And this is a laser and fusing the metal powders over here. And because of there are large process variations, so it can be we can do the LPBF in the laboratory settings, but when it comes to the real-world manufacturing settings, it's not good for mass production because the yield is too low, throughput is too low, because 7 parts, only 3 of them are defect-free. So the cost is high. So what we did is in Sims 3D, we developed the optical imaging system. This is by one of the co-authors, Ted Russo, and Sims 3D researchers and scientists. And we installed the DSLR camera inside the additive manufacturing chamber. So every time we spread one layer of the powder, we take an image, and every time we finish one laser sintering, we take an image of the finish of that layer. So then, based on the layer-wise image, we will be able to do the sensor-based data fusion. So the data fusion will extract useful information about the defect levels of this layer. So if we find there are high levels of defects in a particular layer, then we can control the process. We can either come back to do the laser refusion, or we can hybrid manufacturing machine give us the opportunity to just machining off the whole layer. Then we cannot wait till the build is finished. Then the defects will be embedded in the parts. We cannot do anything. So it will be better if we do the control actions in each action, in each layer, to make sure every layer achieves high quality, so that if one part has 100 layers, then we want to make sure every layer is finished with manufactured with high quality, so that the final part is defect-free. So, but there are several technical issues. First, there is a sequential. This is a sequential decision-making problems, because if you are going to do control one layer, and this layer is going to impact the next layer. For example, if this layer has high defect, and it's very possible the next layer is going to have high defect because you're building upon the defects. And then all the subsequent layers. Okay, so this is a sequential decision-making problem. So that's why we propose Markov decision process for sequential optimization of the AM build quality. So before we go to the next slide, first, it's very important that we extract the defect information in each layer of the build. So how to characterize the defects? That we use a technique called multifractal analysis. So what is multifractal? So now let me give you some illustration on what the fractal idea is. So as we can see here, we have this 4 square box. If we do the perturbation, okay, on the middle of each box, and this is random perturbation. Okay, sometimes it's getting lower and higher, and we do the perturbation again in each grid. Then we got this, and this is called the middle point displacement, random displacement problem, and it's actually the iterative function system to generate the fractal. So if we keep doing it, and as we can see, eventually we can generate a simulation model that is very much look like a mountain. Okay, and the fractal is used to generate the geometry of the real world system, or real world mountains and real world trees, and based on the self-similar behaviors, and we are using the iterative function system to generate the self-similarity, because we're doing the middle point displacement on each grid, and we're doing it again and again in different scales. And the fractal is widely used in Hollywood to do the movie and do the animation movies, and try to simulate the fires and mountains. So what we are trying to do is to develop a new fractal methodology to characterize the defects in the additive manufacturing for each layer of additive manufacturing. As we can see, we can do the defect characterization in different scales. So this is a large scale, and we can get into much finer scales like this, and then we can even go further. So if the distribution of particles or the quality in each area is different, and we're characterizing the defects in each grid. So as we can see, and there will be different behaviors if the distribution of the build quality is different. And we have a paper on how to do the multifractal analysis of imaging profiles for characterization and detection of defects in additive manufacturing. So basically, we are looking at each layer in multi-resolution and try to characterize the geometry in each layer. And then based on the distribution, multi-scale, multiple spatial scale distribution, we are trying to characterize the defect. However, if let's have a look at the defect state estimation. Suppose the defect level, this is a failure threshold. That means if the defect level exceeds the failure threshold, then if we don't do anything, this part is going to fail. And this is the present time. This is all the past layers. So each layer, for example, up to this point, we have already built all these layers. And based on what we have right now, we can predict the distribution of failure in the next layer. And then what's the probability it will exceed the failure threshold. Okay, then based on this probability, we will be able to do the sequential optimization of additive manufacturing. So this is a transition probability from one layer to the next layer. Okay, and so that we can, once we have the next layer, we can do the next the layer after. So in this way, so x-axis is a layer index, and the y-axis is the defect level, and this is a failure probability. So if we finish the ith layer of the build and we connect the sensor output, and then we can update what's going to happen to the next layer, predict what's going to happen to the next layer. Then based on the reward function, we have a decision agent to choose the optimal action. The action is going to help us to reduce the failure probability in the upcoming layer. Okay, what we should do in this layer to reduce the defect in the next layer. So the state is defect signals. Action, we can take corrective actions, or we do nothing is an action too. Right? We can wait or do nothing. And here we only consider two actions. Either you take corrective or you don't do it. You don't do anything. Okay? And the cost. First, if you're going to do the corrective action, there is a cost because you're going to machining off the whole layer. There's a certain cost with that layer. If you're going to do too many corrective actions, the finishing time of this build is going to be prolonged. And if you're going to wait, there's a potential waiting cost, and that will also be failure cost, because failure cost is usually higher if you have embedded defects in one layer. Then eventually this build fails, and that failure cost is very high because you cannot use that whole part anymore. And this is a value function we use to optimize to perform the sequential optimization of AM build. So now let me skip the mathematical part. Let me just interpret the results we got. So this is a layer index. In this build, we have about 100 layers, and this is a defect level. In each layer, we have different kind of defect estimation. Because this is a process, it's a random, it has variations. Manufacturing process has variations, uncontrollable variations, as we discussed. So this is the optimal control policy. So when the defect level, when this level is above this limit, then we take corrective actions. If not, we over here we wait and continue the observation. So we also studied this is a layer index, and how the policy surface is going to change with respect to different layer indices, and also cost ratio, the failure cost over the action cost. So as we can see, this is a log scale. If the failure cost is very close to the action cost over here, right, then the limit is higher. That means failure cost is not that high. Okay, so the control limit is higher. But if the failure cost is significantly higher than the action cost, then the limit is much tighter. We have much lower control limit. So this is because failure cost is very high. We need to take every possible actions to control the quality of the build. Okay. So for technical details, you may refer to the paper I put it in the previous slide. And there are technical aspects and also algorithms available for sequential optimization of AM builds. Okay, so far we finished the first case study on sequential optimization of additive manufacturing. So in that case study, we are going from data to information, to defect information, and then to the knowledge about the defects. And then we leverage the information defect state, and we try to do the sequential optimization of AM build. Okay, now let's move on to the next case study on smart and interconnected manufacturing systems. And this part of the talk is based on this paper published in Journal of Manufacturing Systems. So before we dive into technical details, let me ask one question on what do you think? Okay, what kind of innovation will have the most disruptive impact on manufacturing in the next decade? Okay. So this is a question on what innovation will have the most disruptive impact on manufacturing in the next decade. Okay, if you have any thoughts, you can put it in the chat box. But let me guide the thinking a little bit. Let's look at what is available in the past. Okay, let's first have a look at this picture. So what is this? Okay, and this is a railroad system, right? Railways, and railways is was very big in Pennsylvania many decades ago, many years ago. Okay, so it actually helped the economic growth in Pennsylvania too. Okay, and not in Pennsylvania, but also in the country, in the whole world, to transport goods and people. Okay. So this is the first one. Now let's look at the second one. What is this one? This is electricity lines, power lines. This is electric power grid. So this one brings lights and help the industry, right, with energy. Now let's look at what is the next one. This is, if you can recognize this one. Oh, this one has words on it. It's called radio. Okay. So nowadays people are using their phones for radios. Now this one, most people don't use the old style radio anymore. But this one was very popular before because people can hear news from the radio. So we can broadcast news to a large group of audience. Okay, what is this one? This is old-fashioned TV. If anybody can recognize this one. I don't think this one is available in any house, most of the house right now. And here is the box, and this one is to switch the channels. And maybe some younger generation will be wondering, what is this? This is antenna, okay, on the top of the box to receive the signals. And what is this one? Okay, this one is the high-speed railway, high-speed highways, okay, freeways. So transportation. Now, the last picture. This one is, anybody can recognize this one? This is optical fiber. Okay, optical fiber for the Verizon Fios network. And some of you have this optical network connected to your house. Now, my question is, we have looked at the railroad, railways, highways, radio, TV, and the power grid. Now the question is, what do they have in common in the previous slides? So this is a question. Anybody have any thoughts? What do they have in common? So if you have any thoughts, please share it in the chat box. Okay, what do they have in common? Okay. They are from different areas, right? From electric in the, electric power lines, and from transportation, from the communication business, right? So what do they have in common? They are all disruptive innovations in the past that bring broader impact to the society. But in terms of technology, what do they have in common? This is a question I hope everybody can think. Okay, and then we will see what kind of impact we will have in manufacturing. So what do they have in common? They are all networks. Okay? And the networks transform the society. As we can see, the railroad networks, it's more than like 200 years ago, right? So 1800. Railroad networks that brings the transcontinental commerce, that really brings transformative impact to Pennsylvania, and also to all the countries in the world. Okay? And in the 1920, we have telephone networks, and we have audio communications. Also, this is about the network to make people, right, to be connected. And then we have 1930, electric grid. Electric bring broader impacts to the agriculture and also the industry. Now we have Tesla, electric cars. Can you imagine we don't have electricity grid, right? Now, 1930, we have radio networks. Audio to, this is one-to-one communication. Now this is audio to mass audience. Now this is only audio. Now 1940, we have TV networks, video to mass audience. And 1950, we have interstate highways. Interstate highways really now brings broader impact to the economic growth. And we see the trucks, they are running on the highway every day to transport goods to Wegmans, to Target, and to all kinds of manufacturing industry too. So those are all disruptive innovations, right? That bring fundamental transformation or impact to our society. Okay, but now let's think about what will be disruptive to manufacturing. Okay? Let's think about what will bring fundamental changes to manufacturing. Okay, industry, Internet of Things for smarter manufacturing is about the network. Okay, we are not looking at the machines in a single unit or a single machine. Now let's look at the machine, how machines are connected to machines. So this is a cutting machine and desk, and this is also in the FAM lab in Penn State, Industrial and Manufacturing Engineering. We have many machines like this, and for the manufacturing training, hands-on training to our students. But think about it, if we have power meter which can help us to gather the power or electricity usage of the machine. So every time, this is an electric energy profile, power profile. If we accelerate the spindles, we see a spike. And if we have two-way drive Z-axis and X-axis, if we do the cutting, it's going to have more energy consumption. And then the Z-axis. Now this is a monitoring of a single machine. Okay. What about, oh, next slide. What about if we have an IoT module? Actually, we have senior design teams working on the IoT module sensors and how to connect to, how to monitor each machine and how to transmit the information to the cloud. Once it's in the cloud, no matter you are in Japan or Europe, South America, or even North Pole or South Pole, as long as you have internet, you will be able to see how your machine is doing. Okay. Now, what if we monitor many machines in the FAM lab or more machines in the whole corporate or in the whole company? Okay, in the manufacturing shop. They are located at different locations of the United States. Okay, so this gives us a possibility to perform predictive maintenance and process monitoring of our machines. Okay, the applications are more than just predictive maintenance and process monitoring, but on this case study, I'm going to show you how do we build such a virtual machine network, okay, for one case study, that is the process monitoring. So this is a CAD model, and we have end surface and curved surface 1, curved surface 2. And every time, this is a real world signal. Every time we extrude a spindle, we see the signal variations. Then we see the curved surface 1, surface 2, and then we cut the end surface. Then we decelerate the spindle at this end of the manufacturing cycle. Those, we call it machine signatures. And also, this is a machining process. Now let's have a look at the welding process. This is signal we connect from welding process. So if we weld two parts and we see different kind of electric current, and this is, we call it flash welding or electric welding. And as we can see, there's some activities over here. There's huge difference. The amplitude is a little bit different. And those electric currents, those signatures actually tells a lot of information, a great deal of information about the quality of each part. So what if those information are available, right? If we pass to the cloud and we are monitoring the manufacturing process through the cloud. So how do we leverage such data and then derive useful information and knowledge from those data for the process monitoring and control? So a new idea we propose is network modeling analytics to efficiently represent and quantify energy variations among networked machines in the large-scale industry IoT context. So we have new machine signatures. Now we also have database. This is online signatures. We have offline database. So how to creatively to do the data fusion of the offline database and new online signatures, and then do the pattern matching, okay? And so you can have signature similarity between each other, okay? Now, if we have a network, if we're treating each machine signature as a node in the network, then the new upcoming signature will become one node over here. So if this one is consistent with most of the quality build, you will have one cluster. But if there are two well or some other process variations, you have better quality build. You will see each part is embedded as nodes, as a node in the network. Good quality part will be clustered over here. Bad quality part will cluster over here. Okay, and this is one way to leverage the data and to derive insights from the data for process monitoring and control. So load the information, the location will tell us a lot of more information about how the operation is going right now. Okay. Now, first step, you want to do the pattern matching. How do you see, if you have two profiles, how do you compare the similarity of these two profiles? Okay, some people may do the Euclidean distance. You can do this, but obviously this is not right because this is not aligned. And so we proposed to do this is not aligned, and you want them to be aligned like this. You want peak to compare to peak, and the cutting face to compare to cutting face. And so we used something called warping. Warping is align the profile first, and then measure the similarity between two profiles. But in many cases, when you are doing the process monitoring, we're not just monitoring one channel signal. It might be a 3D signal or multi-channel signals. If you plot a three-channel signal together, it will look like a trajectory. And then you need to compare this face to this face and correspondingly. Okay, so we call this spatiotemporal warping or multi-channel sensory signal warping. And this is a detailed warping algorithm. We're trying to do the alignment and then calculate the distance. Okay, technical details are available in the paper. So let me give you some brief idea on how to do the network modeling. Okay, so here this is a warping distance, the similarity between two profiles, and this is a location of network nodes I and j. So if you are going to do a network representation of machine signals or signatures, so you want to minimize the distance. For example, if you have distance between the network nodes, they should be match the distance between the power or signal profiles. Okay, so simply put, the distance between network nodes, because you are using a network node to represent each signal profile. So what we want is the distance between network nodes are minimized. They are the same as the distance between signal profiles. So if we have hundreds of nodes or thousands of nodes, we want to minimize the distance between these two so that we develop a network. Each node is a profile, and the distance actually preserves the distance of a real-world data. So in this way, we will have a network model of each part of each signal profile. Okay, and this minimization problem can be solved by this formulation, but this formulation will not work if we have, for example, tens of thousands of machines, and each machine is produce like tens of thousands of parts. There will be a large volume data, and this method is computational, expensive, and it's not possible to do this network modeling. So what we did is we developed a stochastic network modeling algorithm. So this is a new objective function. We're trying to calculate the gradient, and the gradient is calculated stochastically, and so that we optimize this, minimize the difference between the network nodes distance and the signal profile distance. So previously, the computing tasks are executed sequentially, okay, one by one. Okay, we have several machines. You do it one by one, and then you do the network modeling. But our new algorithm to tackle the large-scale IoT in the large-scale IoT context, now we are talking about networks of tens of thousands of machines, not just one. So we need parallel computing to do the network modeling very quickly and very efficiently. So we also develop parallel computing algorithms to make sure the network modeling is done quickly and effectively and efficiently. So this is how to do the parallel computing. We just divided the gradient calculation into multiple cores. So this is gamma 1, gamma 2 to gamma s. Then we combine them together for the gradient calculation. This way, it will help us to minimize the computational burden or complexity to do the network modeling. So we did the simulation study, and this is a power profile, and we have simulated profile, and then we do the warping matrix, and then we do the embedded network. So this is the classical algorithms. It can work till 8,000 profiles, and this is our algorithm. As we can see, the time is significantly shorter and more efficient. But when we go 18,000, this algorithm does not work anymore, or computationally, it will not be able to give us the result. So we're still using our algorithm, but we do serial computing and parallel computing and serial computing comparisons to 180,000. Our algorithm, parallel computing algorithm, is very efficient on 12 CPU cores. And we also, now let's have a look at the cycle-to-cycle network modeling. This is a bar feeder machine, which is available in the FAME lab, which is a factory for advanced manufacturing education lab in the Penn State Industry and Manufacturing Engineering Department. And we are doing the machine samples one by one. They're all the same. Now we accelerate the spindle and the turret, right? And we do the cutting. And then we connect the profiles. And then we monitoring the energy consumption. Then this can help us to reduce, if we can monitor and we can see when the machine tool has problems, and then with the process variations, and then we can monitor the quality of product. We can monitor the tool well. And we have normal 3,000 cycles, tool well 1,000 cycles, and chatter 2,000 cycles. The network modeling clearly separates them into different clusters. So this is a virtual machine network. Although each node is not a machine, but it's actually one part after we finish. So these are many parts. It's about 6,000 parts, and we are embedding them in a network. So this is a very effective and efficient process monitoring tool based on the signal we connect from the machine. Of course, this can be extended to different kind of signals, for example, acoustic emission or vibration signals. So if we have wireless sensor signals like IoT, large-scale IoT context. So now let me conclude this case study. So we have big data analytics in large-scale IoT context. So traditionally, we have deterministic network modeling and serial computing, but they cannot handle the IoT, large-scale IoT. So what we did, our contribution is we developed fast parallel network modeling and stochastic network algorithms and parallel computing algorithms. And at this moment, we are also exploring the healthcare case studies and the supply chain and manufacturing. We have one more paper on healthcare coming, and on network, fast parallel network modeling in healthcare. And but this network modeling, basically, if we have large-scale IoT, it can be used for smart city, supply chain, and manufacturing, different applications. So in the end, let me introduce my research team. Without their hard work, those works will not be possible. So my PhD students, they are all award-winning students. So Chen Kan now is an assistant professor at the University of Texas, Arlington. And Bing Yao is still working on her PhD degree. And she got past papers from Informs department and also the IEEE and IIE Institute of Industrial Engineering. And this is Jun has graduated right now is an associate professor in one China university. And this is Dongping. Dongping is my first PhD student. And at this time, she's right now the assistant professor at Texas Tech. And Gang Yu is also getting multiple awards from different conferences and societies. And he's now a research scientist in which is called Upper Healthcare Collaborative Research Center, Michigan and Auburn. Now let me introduce my lab. So my lab's name is Complex System Monitoring, Modeling, and Control Lab at Penn State. And our application focuses on the manufacturing and the healthcare. So those are simulation models we developed for the heart, and also simulation model we developed for the General Motors automotive production lines. So these are previous works, all previous works. But what we focus on is monitoring, data connection, and all right now in this case, Internet of Things, IoT sensing. So we put sensors on the machine, and we extract sensors from the production lines and the PLCs, and also the machine. And we get data from the heart and from the body, so that for healthcare applications, for machine diagnostics and prognostics, predictive maintenance, operations management, and for healthcare decision making. So in summary, we do system manufacturing informatics or healthcare informatics. We also do the quality and reliability engineering. And big data analytics, we do simulation models. So those are simulation models we develop for manufacturing and also for the heart. And our goal is for the optimization of the system. First, reliability, prognostics, maintenance, and optimization. Okay. Our theoretical foundation is nonlinear dynamics, statistics, signal processing, simulation, optimization, and control theory. So this is my background. So first step, sensing, and then modeling, and then optimization. Okay. Application areas, manufacturing. Now I'm working on the additive manufacturing in collaboration with Sim3D. And also I'm working on healthcare problems, heart problems with cardiologists in Hershey Medical School and veteran affairs hospitals too. So in the end of this talk, I would like to thank NSF, National Science Foundation, and also Harold Inga Marcus Career Professorship for the sponsorship. Without the sponsorship, all the work will not be possible. And I'm also happy to collaborate with industry, and we also try to extend the works we are discussing on Internet of Things and smarter manufacturing. And as we discussed, the networks transformative impact to the society, and also may bring fundamental transformation to the manufacturing too. I would be happy to collaborate with industry companies to explore further and the future directions in IoT and smart manufacturing. So this is my contact information. Please feel free to shoot me an email or drop me a call. I would be happy to explore future collaborative opportunities. Okay, this is the end of my talk. I will be happy to answer any questions you have. Okay. Any questions? You can drop it in the chat box, and we can also communicate afterwards with the phone or email. And here is my website, and I have a different set of slides and research papers, including those we discussed today, available in the website too. And I got okay, one comment. Okay, thank you for the comments from Christian. Okay, in summary, my lab focuses on the complex systems. So focus on the sensing, modeling, and the control. So that's pretty much my research area. First, leverage the sensor networks we have, and even the large scale sensor networks, Internet of Things sensor networks. And then second step is to do the data fusion and the simulation modeling, like the cyber physical integration. And then the control is the optimization to feedback the actions to the physical world. Okay, that's what our engineers do in industry and manufacturing engineering. And it was great to interact with you today. And if no further questions, and I wish you guys have a good afternoon. And thank you for attending this talk.